Hello everybody, this is Michaela Mooney doing Vertex Edge Graphs 5 Discussion Assignment Part 2. And we are using a different form of recording and writing today, which I'm very excited about. I just got a brand new iPad, and so I'm trying to figure out how to use this program and screen recording. So bear with me if it takes a little bit of practice. I tried to practice beforehand, but you never know what's going to happen. But I'm very excited about this. So today we are using the nearest neighbor algorithm and the sorted edge algorithm to find Hamiltonian circuits. And we used this in discussion assignment part 1. But in part 1, we found the same circuit for the brute force method, the nearest neighbor algorithm, and the sorted edge algorithm. And today we're going to see what it looks like when we get different circuits, I'm pretty sure. I haven't practiced this all the way through, but I'm pretty sure we're going to see different circuits. So, first, we are going to use the nearest neighbor algorithm on this graph to find, starting at vertex A, which is right here, and we're just going to try and find a Hamiltonian circuit, which we know is a circuit that hits each vertex exactly once, except for the vertex it started at, because it also ends there. So I've written down here the rules that we've gone over, just so that way we can keep referring back to them as we find the Hamiltonian circuit using the nearest neighbor algorithm. So, to start, for rule number 1, choose the edge with the smallest cost. So, if we're starting at vertex A, we could go to any vertex from vertex A. We could go to B, which is 90, C, which is 95, D, which is 85, and E, which is 75. And nearest neighbor algorithm says choose the edge with the smallest cost. So we want to choose edge E because that's 75. So now that we've done step 1, let's look at step 2. Continue choosing edges with the smallest cost that connect the current vertex, which we're at E, to vertices not yet visited. So that means if we're at E, we don't want to go back to A because we've already visited A, and that's our starting vertex. So if we were to go back to A, we would close the circuit, which we don't want to do yet. So we're going to look at all the other vertices we could still go to, which we could go to B, which is 70, C, which is 65, and D, which is 55. And we want to choose the one with the smallest cost again. So we're going to choose D, which is 55. Oh, I'm also going to write down, we chose 75, sorry, that's a bad 7, 75, and 55, because we want to figure out what the total cost is at the end. So I'm just going to write them down as we go. All right, so now we're going to keep choosing edges. We're still on step 2. So we're at D, and we can't go back to E because we've already visited E. Can't go back to A yet because even though it's a starting vertex and we're going to go there twice, we don't want to close the circuit yet because we haven't hit B or C. So our options are to go to B, which is 115, or C, which is 130, and we want to choose the smallest cost. So we are going to go to B because that is 115, and we are going to do that a little math right there. And still on step number 2 because we have one vertex and then we have to get back to the start still. So looking at vertex B now, we can go back to A, but we can't do that because it'll close our circuit and we haven't hit C yet. So really, we can only go to C because we can't go back to D, we can't go back to E because we've already visited those ones. So really our only option is to go to C, which is 105 plus 105. And now we are on step 3, which is after visiting every vertex, return to start. So that means we are going from C back to A, which costs 95. So plus 95. Now, so we found our Hamiltonian circuit because we've started at A and we've hit every vertex once and then we get back to A. So now let's calculate the cost of that Hamiltonian circuit. So we've written down what everything is as we were going. Let me quick type into my calculator what our cost is going to be. And the reason we're going to do this is because we're going to compare the cost of this circuit to the other circuits that we're going to find later. So the total cost of this circuit is $485. So we're just going to hold on to that, remember it for later. Our first Hamiltonian circuit looks like this, and it costs $485. So let's go on to our second nearest neighbor algorithm, but this time starting at B. So we're gonna mark B right here. We're doing the same steps as up here, so that's why I have them written in between the two, because we are gonna reference these same steps as we're going. So step number 1, from start, choose edge with the smallest cost. So if we start at B, we can go to any of these vertices. I always want to say vertices, but we're going to choose the one with the smallest cost. So we could go from B to A, which is 90, B to E, which is 70, B to D, which is 115, or B to C, which is 105. And we are going to choose B to E because that one costs the smallest. So next, we are going to continue choosing edges of smallest cost that connect the current vertex, ours is E right now, to vertices not yet visited. So we're not going back to E yet, or back to B yet, because can't close the circuit, don't want to go back to ones that we've already been to, even though it's the starting vertex, and we're going to go back there at the end. So from E, we could go to A, which is 75, C, which is 65, or D, which is 55. So we are going to choose to go to D because 55 is the smallest cost. Still on step number 2 for D, we're going to choose the next smallest cost. We don't want to go back to B because we don't want to close our circuit. We haven't hit C or A yet. We don't want to go back to E because we've already hit it and we don't need to go back. So from D, we can go to A, which costs 85, or to C, which costs 130. And we are going to go to A because 85 is less than 130, and we want to choose edges with the smallest cost. So now, still on step number 2, we are at A, and we don't want to go back to B because we don't want to close the circuit yet. We haven't hit C. Don't want to go back to D because we've already hit it. Don't want to go back to E because we've already hit it. So really our only option is to go back to C, which costs 95. Oh, I haven't been writing these down. 70 plus 55 plus 65 plus 95. All right, sorry about that. Now we're at C, and we are at step number 3 now, after visiting every vertex, because we've hit B, we've hit E, we've hit D, we've hit A, we've hit C, we are going to return to start. So our only option to return to start is to go back to B, which is 105. And so now, let me type into our calculator what this cost is going to be. 65, 95, 105. And that is $390, which is significantly less than what we found at first, $485, but we'll look at that later. We can see we found the Hamiltonian circuit because we go B to E, D, A, C, back to B. So we hit all the vertices once, except for the one we started at, because we hit that, we start and end at that one. So this helps us see that your starting vertex really matters. It affects like we used the same algorithm, but we got two completely different answers. So your starting vertex affects what your total cost is going to be. Now, let's move on to sorted edge algorithm, which has a different set of steps than the nearest edge algorithm, but similar idea where we're trying to use lowest cost edges to give us the lowest total cost. So let's look at what we have to do. First, we sort edges from lowest cost to highest cost, which I've already done for us here. And then we are going to add edges to the circuit one at a time in order of increasing cost. So that means we want to start with our lowest cost and go to the next lowest cost, next lowest cost, next lowest cost. All of these, we're going to move up from lowest cost to highest cost, trying to add the lowest cost edges to our circuit first. I'm going to read step number 3 right now, just because it's going to come in handy once we get going, but I'll come back to it as we come across this problem. Skip edges that cause 3 edges at a vertex or create a circuit that doesn't include all vertices. So that means we can't just use the first 5 edges to create our Hamiltonian circuit. It's not always going to work that way. I have yet to have one that works that way, but so that's why it's saying this, because some of these are going to cause us problems and we're going to have to skip them. But step 4, just keep going until you have a Hamiltonian circuit. So let's get started on our graph here. We are going to add edges to the circuit one at a time in order of increasing cost. So we are going to start with our lowest cost. I'm going to highlight the ones that we're using, and then I'm going to cross out the ones that we aren't using. So we're for sure going to use this first one because there's nothing on here that's going to cause us to have 3 edges at a vertex or create a circuit that doesn't include all the vertices yet. We have to start somewhere, and the best place to start is the one with the lowest cost. So we can start from E to D, which is 55. And we can also add C to E because it's not going to add 3 edges at a vertex yet because we only have 1 edge on there. So we can do C to E. But now B to E is going to cause us some problems because if we add B to E, we're going to have 3 edges at E, and that is not going to allow us to have a Hamiltonian circuit because we only want to hit this edge once and leave from it. If we have 3 on here, we're going to end up coming back to it, but we can't leave it again. So that's not good. So let's go ahead and cross out B to E because we cannot use that one. But we also cannot use A to E because it's going to cause the same issue. It's going to make a 3rd vertex touch E. So we can't use that one either. Now let's look at A to D. This one is not going to cause any problems because D only had 1 edge touching it. So a second one is actually what we need. And then we are going to do B to A. Let's look at what that does. No issues there. A needs a second edge touching it. B doesn't have any touching it yet. So that knocks out 2 of our problems. C to A. Let's look at that. This one, if we went here, yes, it works at C because C only has 1 edge touching it, but A would have 3 touching it, so that would not work. So we cannot use C to A. Let's look at B to C. B to C would end up completing our Hamiltonian circuit. So that is one that we want to use because we've hit all the edges once now, or all the vertices once, sorry. And we will end where we started, no matter if we start at A. We're going to end at A, C, we're going to end at C. So we have followed all of these steps, and we kept going until we had a Hamiltonian circuit. Now let's find our total cost of this circuit. We can just add straight from our list down here. So 55 plus 65 plus 85 plus 90 plus 105 equals, let me type that into my calculator real quick, 55 plus 65 plus 85 plus 90 plus 105 equals 400. So, let's look at all of the things that we've done. We have used the nearest neighbor algorithm twice, and we got two completely different total costs, two completely different Hamiltonian circuits, and all just because we started at a different vertex. Now, if we look at our sorted edge algorithm, we also got a completely different total cost and a completely different circuit. It's like a mirrored version of this one up here, but we still get a pretty different total cost just because of where the numbers are placed. So even though the circuits, let me zoom out a little bit, even though the circuits are mirrored, like they look like little fish, it shows you no matter like where you start really affects your total cost. So you might have to do some experimenting if that's your main goal, because I mean, algorithms, they are quick, but you're never guaranteed to get the lowest cost. So we really don't know if any of these are, or if this one is the actual lowest cost. We would have to use the brute force method to figure that out. But that takes some time, whereas these ones, once you know how to do them, you could do them in like a minute almost, or maybe even shorter. But yeah, our circuits, this one is the most different. These two are like mirrored images of each other, but we've learned that this one's the cheapest because we used cheaper edges, and just because of where we started, that's why it's cheaper. But yeah, so that's what we've learned. Where you start is important. We can't know for sure if this is the cheapest way without using the brute force method, but these are all great algorithms for you to get a good answer in a short amount of time. So thank you so much for listening to me and for bearing with me as I figured out how to use this new program. I think it's super cool, and I hope you enjoyed it, and thank you for listening, and I will see you next time. Bye!